The final topic for chapter 12 that we want to talk about is catalysis. So a catalyst is defined as any substance that increases the rate of a reaction without being consumed. So what this means is this is something that participates in the reaction mechanism. This is a substance, atoms, molecules, ions, whatever it is, participates in the reaction mechanism, but is not part of the overall reaction. What a catalyst does functionally, how you increase the rate of a reaction is you lower the activation energy. So the activation energy for the reaction changes to something lower, and how that happens is by changing the mechanism. So we have this kind of diagram over here where, this idea that we've kind of looked at before, that you can have, say, this big overall process where you have a really big barrier, and then you eventually get down. But that's a really big barrier, so it'd be a really slow process. Instead, with a catalyst, you fundamentally change how the reaction happens. It goes through a new mechanism, which is possible because you have this new substance that's present. And instead of, say, one big reaction with, say, one single collision with a really high barrier, you make it multiple steps. 1, 2, 3, 4. Each of those steps still has a barrier, but importantly, they all have lower barriers than the one single step. And so overall, we would say, or overall, the reaction becomes much, much faster because the catalyst changes the mechanism to go through steps with lower activation energies. So there's a video that's also posted showing a supersaturated solution of sodium acetate. So, you can imagine you can use temperature, you can heat up a solution of sodium acetate, you can get a lot of it to dissolve, and then when you cool it down, it should go from being ions that are dissolved in solution to being solid, to leaving solution to forming a precipitate. But the whole point of this is the kinetics, that this process is very slow. So you have a supersaturated solution that just stays with the ions dissolved in solution. It should be happening, but it's a really slow process. And the reason why it's really slow is that the activation energy is really high. And so how you can change that is change it to a different process. When you have just a supersaturated solution, you have, say, just these ions that are floating around in solution, and in order for them to form a solid, you would have to go from ions to creating a new solid crystal. And there's a really high barrier to doing that, to go from being isolated ions to all coalescing together into becoming a solid. And that's really, really difficult it has a really high barrier. So if you change it, you add a catalyst, you add just a piece of solid, now you're changing the mechanism. Instead of just having ions that collect together to form a crystal, instead you're growing a crystal, right? So you're growing a crystal off of this seed. This is something you put in, and you are changing the mechanism because you're changing it from forming a new crystal to growing an existing crystal, which has a lower barrier and therefore happens much, much faster. And you will then do what is supposed to be happening, which is namely all of the sodium acetate leaving solution and forming a solid. The same kind of idea can happen when you're heating water. So water can superheat above a boiling point. It can get really, really hot. It can go above 100 degrees Celsius because there's a relatively high barrier to forming a bubble in solution, or in the liquid. So just in the liquid forming a bubble, it's hot. It's hard to do that. So you have to get above 100 degrees Celsius in order to go over the barrier. So you use boiling chips. You'll note there's a little thing in here. You put a little solid in there. You put a little solid into the liquid. And now you're forming a bubble on the surface of what is generally a rough solid. So you put a solid that has a rough surface. You'll also may notice if there are scratches on the glass, that bubbles would preferentially form on that scratch or on those cracks. That's a good way to diagnose cracks in a piece of glassware. The reason why we then use this, you'll use boiling chips, you'll put something in like a stir bar in a solution or in a liquid when you're heating it, is because otherwise what'll happen is you let the liquid gets overheated. The liquid gets superheated above 100 degrees C. Eventually, it gets really, really hot, and you're able to overcome that barrier. And then, boom, all of it starts boiling violently, all at this elevated temperature. Generally, it's close to 108 degrees Celsius, which is much hotter, and then causes some issues that you get rapid boiling. That's what happens when you get something that boils over. So you can put little things in there, boiling chips or something, to prevent that from happening, because you're changing the mechanism. Instead of forming a bubble of air or bubble of steam in the liquid, you're forming a bubble of steam on the boiling chip. If we return to our idea of painting cars, we saw that water increased the collisions. The number of collisions made them easier to happen. Salt is a catalyst for oxidation reduction reactions. So if instead of just having water, you have an electrolyte solution, now you have electrons flowing. So instead of requiring the electrons to flow literally between atoms on, say, the metal and whatever's there, the oxygen that's present, the electrons can now flow through a solution. And so when the electrons are flowing through an electrolyte solution, that is, say, salt water, they'll flow more easily. The mechanism changes because the electrons are flowing in a different way. They are flowing through the ions still in the solution, and your reaction happens much, much faster. And that's why rust happens more quickly when you have salt water that gets onto the vehicle. When we're dealing with catalysis and we're designing this, the catalysts that we use can have two different classifications. First, we have homogeneous catalysts. Homogeneous catalyst is any sort of substance that is in the same phase as the reactants. So oftentimes these are both dissolved in water. This is really common in a laboratory setting. So say you have reactant 1, reactant 2, you can imagine that they're going to, say, do a single collision and then form this product. So that would be your uncatalyzed or non-catalyzed high energy barrier. Instead, you can have, say, this big catalyst here. And so what can happen is this catalyst then forms, say, a molecule usually, and it forms a connection or forms a reaction with, say, I think it goes first with reactant 1, so it forms a complex with reactant 2, then reactant 2 comes out and attaches on, you break that bond there, and then all those atoms, say, reform and make the product. And so that catalyst is then a molecule when it's homogeneous. So generally these are molecules that are reacting with your molecular reactants. We use homogeneous catalysts in a laboratory setting. You have a lot of fine control of reaction. Generally, you're doing everything that's dissolved in water. You can kind of get it out. But you'll note the catalyst doesn't change, importantly. It starts out as this big molecule. It ends up as still the big molecule. And importantly, you don't need a lot of catalyst because that finished catalyst, the one that is done with the reaction, it can react with more reactants. So that's also why the amount that's present doesn't matter for your rate. It's just kind of there being replenished because it's not consumed in the reaction. You can go right back here and do it again. A heterogeneous catalyst is then one that's in a different phase from the reactants. So a common example of this would be a solid surface that you flow liquid or gas reactants over it. Heterogeneous catalysis is really, really common in industrial settings. So for example, you can just have, say, your metal surface, and then what you do is you just flow your reactants over it. And this is really useful in an industrial setting where you have, say, tons of reactants that are flowing over the surface of, say, a metal, and they're doing a reaction on that surface, and then they just keep flowing over it. Every car that's been made in the past, say, 30, 40 years now has a catalytic converter on it. The purpose of a catalytic converter is you have gases like carbon monoxide and NO, which are bad for humans and bad for the environment. They flow into the catalytic converter and they are turned into either N2 and or CO2, which are much more benign for the environment and much less dangerous. So this decreases smog and dangerous air pollution. And basically how the catalyst works is it's made of platinum, rhenium, and rhodium, which are all transition metals. And you can use platinum as kind of the standard version. And so what happens is the gas molecules will come and attach onto the surface, and then what can happen is you can break the bond when it goes onto the surface. So an oxygen molecule is not just going to fall apart in the gas phase, but when the metal surface is present, when the molecule comes onto the surface, it will break into individual atoms. Those individual atoms can then interact with, say, other gas molecules like carbon monoxide that are potentially attached onto the surface or that are interacting with the surface, and then that can leave as carbon dioxide. And so it is really unlikely that a collision in the gas phase would have, say, this carbon atom of the carbon monoxide taking or reacting with an oxygen from the O2. That'd be a lot of energy. It's very unlikely for that to happen. But on the surface, because the oxygen molecule is broken when it interacts with the surface, that reaction becomes much more likely, and the barrier becomes much lower, and the process becomes much faster. And by that I mean it happens at all. So let's look at an example of analyzing a reaction where a catalyst is used. So we got a reaction mechanism. H2O2 plus HBr becomes Br2 and H2O, and then Br2 plus H2O2 becomes HBr and O2. So I want to know, what is the overall reaction, what intermediates are present, and what is the catalyst?
So if I want an overall reaction, I know I'm just going to add everything together. So let's write out what we got. H2O2 plus 2HBr becomes Br2 plus 2H2O. Br2 plus H2O2 becomes 2HBr plus O2. So I'm going to put all the reactants together, H2O2 plus 2HBr plus Br2 plus H2O2. So that's just all the reactants together, Br2 plus 2H2O plus 2HBr plus O2. Gotten everything written out, I want to go through and eliminate anything that shows up unchanged on both sides. So H2O2, there's H2O, but no H2O2. 2HBr, 2HBr, so that shows up on both sides. Br2, Br2, yep, that shows up on both sides. H2O2, again, didn't show up anywhere else. So I can cancel out things that show up on both sides, and I can combine doubles. So the H2O2s that were right there. Okay, so I can take that. Overall, I can put everything together now. That is 2H2O2 becomes 2H2O plus O2. And that is my overall reaction. So when I analyze overall reactions, I also want to be looking for intermediates and catalysts. And so when I go back and look, intermediates and catalysts, it's not going to be any of these things. Anything that shows up in the overall reaction is not intermediates, not a catalyst. They are called reactants and products. So intermediates and catalysts are going to be things that we eliminated along the way. So when you're looking for candidates for those two, you want to look back to your work for this and find the things that got eliminated. So the candidates would be Br2 and HBr. So anything that gets eliminated in this process has to be either an intermediate or a catalyst. And how we can tell the difference is we can look back up to the steps. HBr starts as a reactant. That means it is present before the reaction starts. You add it to the reaction process. So it shows up, if we go sequentially, we start at 1. We see that HBr starts as a reactant. It then, in step 2, is a product. So you add it to the reaction mixture. Those bromine atoms participate in the reaction, and then you get HBr on the back end. So that means HBr is a catalyst. Acids are often catalysts. What intermediates are present then? So when we see Br2, we can see that if we follow kind of the trend H2O2 and HBr form Br2. So the first time we see Br2 in the reaction mechanism, it is a product. After being a product, it is then a reactant in the next step. That is indicative of being an intermediate. Intermediates are formed during the course of the reaction mechanism. They are not present at the beginning of the process, and they're not present at the end, right? It is made and then consumed. A catalyst is consumed and then made. And so those are the differences. So the reasons why we differentiate those is you are adding HBr to this reaction. You are using it to drive and to cause this reaction to occur. Br2, bromine, you are not adding bromine molecules to this. Bromine molecules are made and then they get consumed and they go away. You are not using that. That's not something you would add to the reaction mixture to affect or drive this particular reaction mechanism. So that's why we want to differentiate these two ideas, because one of them you use, you add, the other one just passively forms in the process of the reaction happening.
Okay, no participation questions in this video. One video left in this set. End of chapter 12, end of week 4, end of material on next week's exam. I'll see you there.